Yeah, you can go ahead whenever you're ready.
I'm just sharing screen. You can see my screen.
Yeah.
I'm Taruna Verma, and I'm about to graduate with Masters in Data Science. And today I'm going to talk about breast cancer. This project is funded by NSF, and the findings presented in the work are authors and do not reflect views of the funding institution. So the research started with the project aimed to develop a framework for a culturally appropriate and privacy-aware tutoring system, wherein the tutoring system is a mechanism wherein it's basically provide information to the user, but when there's another team who's taking care of it, but then eventually we realized that there should be a chatbot system wherein user can also ask questions. So this has been designed to educate breast cancer survivorship skills to low literacy Hispanic breast cancer survivors. So I am building a chatbot wherein the user can ask questions related to breast cancer. I'm going to talk about this part of the chatbot module. We all know that breast cancer is one of the most common cancers, and it is far more prevalent in women. It occurs when cells in the breast begin to grow uncontrollably, forming a tumor. And the early detection is the key to survival. So, while it advances in research and treatment options have significantly improved survival rates, breast cancer is one of the very, I think it lies at top two level when it comes to cancers. So why would we need chatbot for in this research? Chatbot is going to increase access to health information. There are many people, especially those from marginalized communities like Hispanic community, who struggle to find clear and trustworthy information about healthcare. So a chatbot will help them to look up for any information related to breast cancer. It's going to address low literacy. Basically, this is designed for Hispanic population. Hispanic breast cancer survivors in particular may face language and literacy barriers when accessing health resources. This chatbot will simplify complex medical language and present information in easy to understand format, which will help users to make informed health decisions. The chatbot can answer questions instantly and accurately, providing real-time responses to user. And this will reduce the time spent searching for information on any search engine. The chatbot serve as a tool to educate users about breast cancer, from symptoms and diagnosis to treatment options and risk factors. It also empowers users with knowledge, which can lead to better outcome by encouraging early detection and timely interventions. So I'm going to give you an overview how does this chatbot works. So the breast cancer chatbot provides reliable AI-driven information about breast cancer, including symptoms, diagnosis, treatments, and risk factors. It uses a combination of NLP models to answer questions and offer helpful resources. The goal is to answer user queries with relevant information and guide user through a personalized experience based on their profile. And it provides accurate resources and follow-up questions related to breast cancer. The main key features of the chatbot that I am building is that it answers real-time questions. There is typo detection and suggestions. The chatbot uses fuzzy matching techniques. There's a tool called fuzzy to detect and correct minor typos in user queries. There is human in the loop for quality assurance. There is an interactive user interface, and then continuous learning and feedback logging. I'll explain each of them in a few seconds. The key technologies being used is Python. I've used Streamlit. I'm going to deploy this on by using AWS. I've used transformers, which is utilized to load the Distilbert base-cased distilled squad model for question answering tasks. Sentence transformers are being used for semantic search. Fuzzy Wuzzy, as I said, for the typo detection. The pandas is being used. And then I'm going to use AWS for deployment. And NLP, natural language processing, is the whole. Now, let's discuss how the chatbot is being designed. There is a user interface which is being designed on Streamlit. It provides a clean and interactive user interface. So user interacts by typing their question and receiving real-time responses from the chatbot. There is a question processing. There are pre-trained model, Distilbert, and sentence transformers, which are used to process and answer user questions by analyzing the relevant context. There is a knowledge base, which is a predefined set of breast cancer related information. So the user can ask questions related to breast cancer. If there is like any irrelevant question is being asked, the chatbot will say this is not a relevant question for this. And going to provide accurate and comprehensive answers. So there is context retrieval, embeddings generation. User queries and knowledge-based content are converted into embeddings by using sentence transformers. And there is cosine similarity. The most relevant context is selected based on the similarity between user queries and the stored knowledge base using cosine similarities. There will be personalized responses. In the beginning of the chatbot, there is a user profile wherein user inputs their age and family history to deliver a personalized advice and recommendations. Then there are follow-up questions. So when the user asks a question, there are similar kind of questions being suggested so that if the user is interested in the same uh, um, type of questions or knowledge. Then there is logging feedback. User feedback, helpful or not, on chatbot responses is logged for continuous improvement. So at the end of when the user gets an answer, they can give their feedback as thumbs up and thumbs down, and then that feedback is being saved in a CSV file so that we can use it as a human intel system. Then how I'm handling the user profile. So the whole purpose of having a user profile is that the chatbot collects user information and then gives the personalized responses. The question being asked are age, um, family history, risk factors, and then saving that data into CSV file so that we can use the CSV file later on. Profile-based customization, as I said, but for if the users are over 40 and they are encouraged to start regular screenings based on the user selected risk factor, they receive tailored advice. The goal is to help users make informed decisions and take proactive steps towards their health. The interface customization, the chatbot's interface is designed to be clean and user-friendly. There is a custom CSS styling, which is used to enhance the readability of chatbot's interface, which includes background colors, text styles, and button designs. There are elements, for example, the user questions are being displayed with a blue background for easy identification, and the bot responses is displayed in a white background boxes. And there are follow-up buttons. There is thumbs up and thumbs down emoticon for the easy feedback login. And the knowledge base, which is going to help with retrieving the data. There are core topics like what is breast cancer, what are the symptoms, diagnosis, treatments, and risk. Each section is predefined with concise information regarding that category. So each question is matched with a relevant section from the knowledge base using semantic similarity, and then it gives the response. The information is dynamically retrieved based on user's query. For the typo detection, when the user types a question, the system checks for typo using fuzzy wuzzy matching. And then if the errors are found, the system can suggest corrections and automatically fix them. And then once the query is corrected, the chatbot proceeds with semantic search and question answering as usual. For the question answering system, the model used is Distilbert base cased Distill Squad. The process is once the most relevant context is identified, the model processes the question and context, providing a precise answer. If the context is too short, additional details are fetched from the knowledge base, and the extra resources link is being provided, and the user can go to the link and read more about the same topic. For the semantic search, um, we use sentence transformers to match user queries to the most relevant text in the knowledge base. For the catching mechanism is implemented to speed up the retrieval process. How human in the loop is the process is being used here is that the user feedback thumbs up or thumbs down. There is a collection and the data is being saved into CSV file. For every negative feedback, responses with multiple negative feedbacks, they're flagged for human review. So if there are a lot of negative feedbacks, thumbs downs, and when the user asks the same questions, it should not show the negative answers, but should change it. For the manual review, human experts review the flagged responses and then suggest improvements. After each interaction, users are provided feedback. As I explained before, user can rate their responses and then it is being saved into CSV file. The feedback is stored in a CSV file that includes question, responses, feedback, and types. For the continuous learning and model improvement, feedback from users and human expert is used to fine-tune the model. The model gets updated periodically with new, more accurate data. This is one of the things that in the future we can add more real-time data into the chatbot. The benefits are continuous learning from real-world data, improving response accuracy over time, and for better user experience. This is how the chatbot looks like. Initially, the user can input its information, the age, and if they have any history or not. If they say yes, then these are the following options they get. Once they click it, the profile is being submitted. It says profile data saved, and then user can ask questions. Once the user has asked first, for example, they asked what is breast cancer, it's going to suggest different questions here too, which the user could be interested in. And then the learn more, if the user will click on the learn more, it's going to direct it to the resources, different resources online. And then the user can click on thumbs up or thumbs down according to how they like the response. The challenges are ensuring that the model gives accurate response for complex medical queries, and then collecting sufficient feedback and handling flagged responses efficiently. One more challenge I would say is to get the real-time data to train this model more accurately. And the solutions could be continuous feedback loop and manual review by healthcare experts, regular updates and retraining of the model with new data. And for the real-time data, there is another team that is working on how to get the real-time data from patients. Future enhancements are, as I said, this is designed for Hispanic population. I don't know Spanish much, but there is another team who's working on the Spanish side, and in a couple of weeks, we are going to integrate that. So the bot will have Spanish and English both options. Then integrating more healthcare data, as I said, there is a set of team who's working on getting the real-time patients data, and then we can integrate it together. And advanced personalization, tailoring answers based on user profiles. Once we have the real-time data, we can train the bot for getting the same kind of tailoring answers. And then the tutoring system that is being designed, I explained in the beginning. we are going to integrate this chatbot into the tutoring system so that when user wants to ask question, they can use this chatbot. So the summary, I would say the chatbot enhances user access to breast cancer related information. There is a continuous learning which ensures responses improve over time, and the real-time feedback and human review are essential for a quality assurance. I would like to thank you for your time and attention, and I really look forward to the opportunity to take this project further and improve access to life-saving healthcare information. I'm really excited to try this chatbot with the real-time data. Once the team has it, we're going to deploy this and test this chatbot.
Thanks, Saruta. Let's go on. Shreya, are you ready? All set to go? And then Jiasheng, just follow immediately after Shreya finishes up.
Yeah, sure.
Yeah, let me share my screen with you. So are you guys able to see my poster?
Yes.
Yeah. Well, hey everyone, I'm Shreya, and under the guidance of my professor Amit, I have done a research regarding this LLM for adaptive systems, where we have created a lightweight LLM model by totally it's an offline system, and we have diagnosed this into the Raspberry Pi. So basically, we have created a sensor fault detection here, where I have used like question and answer system where the user interface has it. Like I have used the prompt engineering basically. And coming to the introduction part, yeah, 1 second. Yeah. Firstly, I have took the IoT sensors and the synthetic data where the CSV files into this will process in the MATLAB thing. MATLAB will proceed with it and gives like it pre-process it with missing values and noises, and then it sends to the like model training where I have created a model training by I have used Bayesian optimization by not collecting all the random values over here. So that I have also used Adabus classifier to train the model. And this and simultaneously I have created a prediction class too. So that where I have created a classified data. That classified data goes into the questionnaire. Then the model has trained it according to the sensors that detect in the real time environment. The model gets deployed into the Raspberry Pi directly. Then it gives a classified data to a user. So this is our basic point of view of our project. Then coming to methodology, here I have generated a synthetic data which contains all the CSV files, which MATLAB reads it as the inputs. Then I have trained a Adabus model here with hypertuning it. Then I have exported the trained model where I named it as a sensor fault. Then I have exported this trained model, which creates an ELF file through the MATLAB directly into the Raspberry Pi. So that I need not to be exporting the files and everything into the Raspberry Pi without any manual work. I have also used LLM here, like Penny Llama. It is a lightweight model running offline via Llama. It enables natural language processing too. I have created a final assistant script which supports real-time sensor queries, human readable explanations, and this is actually designed for this LLM actually integrated because like so as to have the fast and low latency prompt execution. And coming to the integration, I have 1 second. Yeah. So basically, synthetic data which has the CSV data sets reads the files into the MATLAB, then exports the ELF it exports as the ELF format, which is generated by the MATLAB. Then coming to the Raspberry Pi part, I have created a Python script which I have used like chatbot AI, so that it reads all the questionnaires which is prompted by the user. Then then the Python scripts reads the new inputs and append output to the user prompt. Then LLM module processes the prompt, and it redirect to the user interface. The user interface just displays the like sensor faults which is required for the person. So basically, this project can be used mostly in the agriculture sector, where the farmers need to have the access like everyday access, like constant information about the temperature and humidity. This temperature and humidity is observed or collected by the farmer or the person who is not available in the farm, so that he has to have a person in the farm. But here, without any intimation or without anything, any person in the farm, the AI, the model is going to the, like, we are going to create a user interface for a person, the physical person, who will give the user prompt as what is a sensor fault. Then he gets the information as so now the temperature is 32 degrees, so your crop can be cultivated now. This is the way the user gets the prompts. And coming to the, like, Raspberry Pi, we have integrated all the stuff into the Raspberry Pi. We are yet to integrate the sensors in it. So from my end, I have already integrated all this stuff. My with the help of my professor, I'm going to integrate this sensors into this, because I have no idea about the sensor actually. So, and the dashboard basically updates every 5 seconds of data. Since if you take like 1 hour of like data, it may vary the accuracy, so that's why we have to 5 seconds, so that it might predict the sensor fault accurately. So in future, we also gonna, like, we are like, we can also create an application through this, not only the user interface thing, we can also have an application. So this is my project, and this is my learning for so far, actually.
Thanks, Shreya.
Thank you.
Yeah. Hello everyone. So I'm Jashin. I'm from Binghamton University, and my topic is about the enabling efficient mixture of experts, training, and influence on Cerebrus as CS2. And so a brief introduction of the LLM is that the LLM has attracted widespread attention from the industry and the public due to their outstanding performance in many practical language and reasoning tasks. However, the extreme high inference cost is a major obstacle to its widespread deployment. So that's why we raised to the MOE model. So this architecture can reduce its cost by replicating certain model component multiple times while routing each input into a small subset of these replicas. But also MOE training and deploying MOE models efficiently remains challenged due to the increased communication overhead, dynamic expert routing, and the memory constraints. So that's why we are using a new chip called Cerebrus WSE2. So unlike the traditional chips that are only a few square centimeters, WSE is a full wafer scale chip, pushing Moore's law to the extreme. So it contains 2.6 trillion transistors and houses 850,000 specialized compute cores, which optimized for sparse linear algebra, which is a perfect match for MOE workloads. And all memory and the compute are kept on the same silicon wafer, eliminating the off-chip latency and reducing the bottlenecks. And thanks to this architecture, we can get 20 petabytes per second of the memory bandwidth and 220 petabytes per second for fabric bandwidth. And these are these are really large numbers and giving us cluster scale performance on a single chip. So now let's look at a little bit deeper into how the Zebra WSE2 actually works under the hood. So the chip has 850,000 PEs, which are also referred as the logic units, arranged locally in a 2D mesh. And for each PE, it has 48 kilobytes of the local SRAM, and crucially, both read and write operations complete in just one cycle, which enables the extremely fast access. And not just for the local memory, communication between adjacent PEs is also one cycle latency, making the neighbor-to-neighbor data transfer almost instantaneous. And the PEs natively support the 16 and the 22, 32-bit floating points and the integer formats, which are especially important for deep learning and the sparse metric operations. And the computation and the communication are programmed in a data flow model where the PEs operates in parallel and exchange data through a programmable routing fabric. So the routing structure is highly flexible, supporting both the static and the dynamic passes, so which were referred as colors in the SDK design. And the data is transmitted as the wavelet, which is a small packet that travel between PEs on the fabric. Again, only one cycle per hop, so which will enables the efficient pipelining of the data and the compute. So all of this is backed by about 40 gigabytes of on-chip SRAM, which shares across data and instructions and designed for fast global synchronizations. And the key takeaway here is that this fine-grained parallelism and the ultra-fast local memory and communication makes the WSE fabric extremely well suited for dynamic workloads like MOE, where both sparse computation and fast expert routing are crucial. And so this is the comparison for the CS2 with the NVIDIA A100 GPU. So you can see like the really huge difference is the fabric bandwidth and the memory bandwidth. You can like 45,000 faster compared to the A100 GPUs. And it also has like over 100 times larger cores on the Zebra's WSE2. And the current work is on the research is on the testing the high performance of general metric multiplications on the SDK. We are using the Cerebras 2 WSE2 chip on the Argonne Leadership Computing Facilities, which belongs to the Argonne National Lab, and it is the DOE Office of Science User facilities that enables breakthrough in science and engineering by providing supercomputing and AI resource to the research community. And so why is the GEMM so important? So because for the LLM, the self-attention mechanism and the feed-forward networks are implemented using the linear projections. And also for the MOE, that for each expert is essentially a small feed-forward network. And the algorithm we used for the GEMM computing is called the Scalable Universal Matrix Multiplication Algorithm, which is called SUMA. And we are using FMAC or FMAC-H for the global matrix productions, and also we have broadcast operations in both X and Y directions for the communication through the PEs. And just a really quick intro about the Summa. So for the host will first copy the tile of A and B onto their corresponding PEs, and then uses the remote procedure called which is the RPC mechanism to launch the function main. And at each point, the GM will compute begins. So for example, we are using a P times P grid of P's, and for each step I that less than P minus 1, first the P's will from the ith column will broadcast their local tiles of A to other P's in the same row, and same for the P's in the ith row broadcast their local tiles of B to the other P's in the same column. And once the both for this step, once the both broadcasts are complete, each PE will compute C tile for the local AP and BP, where AP and BP are pointers to either the P's home tile or the tile they received through the broadcast. And we have tested the performance for the GEMM on the SDK, and we have used the size of A and B from 33,000 input to 48,000 and 750 48,000. So you can see that there's a really huge difference performance between the 40,000 to 48. So it's from 476 teraflot to 700 teraflot, and because of the limitation from the SDK, each PE only has like 48 kilobyte memory, so we cannot exceed to such amount of 48,000 input per PE. So that is almost the maximum size of the computation we can do on the SDK. So it will have 785 teraflot per second performance. And the future work is looking forward. Our goal is to fully leverage the unique architecture feature of the CS2 to unlock the efficient MOE training and inference. We plan to explore how to schedule experts onto the fabric dynamically, and so that we can minimize the latency and then maximize the PE utilizations. And for the sparse activation strategies, since the MOE, we only activate a subset of the expert per input. And also we plan to explore dynamic load balancing, because which will prevent some experts from being overloaded while others stay idle. And we are also trying to explore memory optimization, which will include using weight streaming, so we don't have to store all the expert weight on chip that will at the same time. So once we have built this system, we will benchmark it against the GPU-based MOE implementations, looking at speed up, energy efficiency, and scaling. So ultimately, we hope our work will contribute insight for scaling large, sparse AI models on the wafer-scaled system like the CS2. So thank you, and that is the our topic and the recent research on the Cerebrus.
So thank you. I guess in the interest of time, we'll go ahead and go to questions from those in the room here. I mean, Eric, you've had your hand up since Jack's presentation at the beginning. Do you want to go ahead?
Yeah. I just had a quick question, a couple quick questions for Jack. So the impression I got from your study was that you were focused on how students are using AI. How do you think that educators and teachers can use AI? Because as someone who's currently working in public education, we've been introduced to like Magic School AI as something that we as teachers can use. So do you think possibly your results would have been different if you if you did a study on how teachers could implement AI for lesson planning or, that kind of stuff?
Yeah, I think the results would have been a lot different because the teachers themselves are the ones getting the AI responses so that they can tell themselves if this is reliable or something they want to use. And that's something that you always use. Like when you look something up on Google to help with a lesson in the past, you might say, oh, that's not useful at all for what I'm doing, but you're making that decision. It's not the student making that decision where the teacher now has to tell if a student used it or not. So I think it would have been a lot different.
William, let's go to you next.
Jack, I had asked my question of you in the chat. Do you
Okay.
just want to go ahead and expound from there?
Yeah, so AI could totally help with the level of the ladder of abstraction that you mentioned before. In fact, I created a little chatbot on School AI to help with this specific one. It would take like 1 second if I'm able to share it. If not, that's okay.
Okay.
All right. Let's see if it works. All right, are you able to see the screen, for instance?
Yes.
Right, so I was able to use School AI to code something on the Boston Massacre to help with the ladder of abstraction. So basically with this is the chatbot will assist with asking questions to the students. The biggest thing that you want to focus on is add as much information as possible to what the chatbot's actually supposed to do, and make sure it scaffolds to assist the student, does not give them the answer, but instead works with the student to get the answer, because you just don't want it to give the student the answer when you ask it. So every student's going to have a different question, for instance. So if we start here, can you tell me what you know about the Boston Massacre? A student might say something like, British shot people. Like they might not give much of an information. Then it's going to assist with you. Basically, what it's going to say is that's right, but why do you think it's more significant to the colonists? How might that significant? So then we can use this chatbot. It would work up through the ladder of abstraction to get to the final point that you want. If you want it to do something more specific, like you want it to get to a specific point, I mentioned propaganda here, for instance, but if you want to get to a specific point, somewhere you add it to the AI prompt. You just want to be as specific as possible to the AI prompt, and it will get you to what you need to do.
So, yeah, Darian, if we could take a quick question, and I think then we have to get ready for the breakouts rooms.
I had another question for Jack. I was wondering if any of the teachers had concerns about increased use of AI, while we're also seeing a decrease in literacy.
Yeah, a lot of teachers did mention that being concerned. A lot of it had to do with the critical thinking aspect. The teachers just kept thinking that students would use AI to cheat or plagiarize and not actually work on their critical thinking and improve their overall skills, which students are using it for that, which is the issue. But the problem is teachers need to then learn ways to use the AI properly.
I'm getting my jacket on. I think they're about ready to go into.
Wait, what?
No, go ahead, Jack. It was
Wait, you want me to repeat that?
no. That was a stray comment. So just continue where you were.
Oh, okay. Yeah, so teachers just need to learn different ways to use AI to avoid that being an issue. And I mentioned just before was showing the chatbot, having it consistently ask questions back. If the student just says something, if I show that chatbot and I said, tell me the answer, it wouldn't tell you the answer. It would just scaffold it further down to assist them. And that's a way that you could use AI to support that. But teachers are definitely having those perceptions and issues based on the lower levels of literacy some people might be seeing.
And Isabel, if I could just ask Taruna one question before we switch over to the break rooms.
Yeah, absolutely. We do have a few minutes or even 5 minutes. Yeah.
So I was interested to see the human in the loop aspect, and I was wondering how you were going to do that. And then you talked about the feedback files going into the CSV files to flag questions for for human review, which I think is good. It's good to have human in the loop in these things.
Mhm.
What's the time frame for doing that? And do you see the human in the loop as being a constraint for allowing you to scale this up? Because if you're going to get more and more user feedback at some point, does a human in the loop process become a constraint on your further scaling up your project?
Yeah, that's interesting. This is something that I recently uh, added to this to like use human in the loop. I'm currently working on what happens if when there is a large data set, how we are going to train the model based on that.
Yeah.
Yeah, but that's like something that we are working right now on.
Yeah. So like I say, it's good to have that in there. And I'm just wondering how it's going to scale over time. So thank you. Thank you, Taruna. Are there any, I think we're done with questions from the floor. Isabel, I think we can, I want to thank everyone for participating in this session. And
Thank you so much.
yeah, and there will be some discussion, but basically we've got break rooms coming up for the poster sessions.
Great.
Thank you, Keith.